Okay, ladies and gentlemen, we are going to look at more geometric series, but today we are not going to look at finite ones. We are going to look at infinite geometric series, so terms that go on and on and on with no end. So let's look at this first one. Can you tell me what S sub 3 is? I certainly hope so. It's a matter of adding three numbers together. 1 plus 2 is 3, plus 4 is 7. Can we find S4? Well, that 1 plus 2 plus 4 plus 8 is 15. Easy enough. Could you find S sub 50 for me? And I hope you're saying, yeah, I can do that. I watched the previous video. I practiced those problems. I'm good to go. How about S1000? Yeah, I could do that. It's going to be real big. But what if I said, find me S infinity. Find me the sum of every number in this series. You'd look at me and you'd say, that's the most ridiculous thing I've ever heard. And a lot of times, you'd mostly be right. We can't do it. We can't add up infinitely many things. But sometimes we can, ladies and gentlemen. For this second sequence, if I wanted S sub 3, you could find it for me. 8 plus 4 is 12. Sorry, 8 plus 4 plus 2 is 14. S sub 4, 15, and we could find S sub 50, we could find S 1000, we could find S sub 1 million if we really wanted to. And I could then say, well, what's the sum of every possible term in this series? What's the sum of every term in that sequence? And you could actually give me a number for this one. I mean, talk about crazy. How does that work? Well, it all starts with our geometric series formula. And these are two very different scenarios. This one, the series is getting bigger. The sequence terms are getting bigger and bigger and bigger. These sequence terms are getting smaller and smaller and smaller. Our common ratio here is 2 versus 1/2. So let's look at what happens if we look at those cases individually. U1 plus, I'm distributing the U1. U1 times 2 to the n over 1 minus 2. What happens, remember this concept of a limit? What happens as n gets really, 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 really huge? Well, ladies and gentlemen, what happens is this thing right here gets really, 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 really huge too. And as n gets bigger and bigger, this fraction gets much, much bigger, and there is no sum. But, ladies and gentlemen, here's the cool thing. Limit n goes to infinity of u1 minus u1 times 1/2 to the n over 1 minus 1/2, what happens to this term as n goes off to infinity? As n gets huge, what happens to a fraction to a huge number? Well, that fraction, ladies and gentlemen, that gets closer and closer and closer and closer and closer to 0. So this term right here, as n gets uber huge, gigantic in fact, that highlighted term is getting closer and closer and closer and closer to 0. So we say that this sum, S infinity, is U1, it's converging to U sub 1 over 1 minus R. And that takes us to this. As n increases, the sum of a geometric series converges to S sub infinity of U1 over 1 minus R. If, and this is a big if, the absolute value of R is less than 1. These terms, these series terms, these sequence terms must be getting closer and closer and closer to 0. They have to be getting smaller, or we will not be able to converge to a certain value. You can think of this sum sort of like an asymptote on a graph. Our sum is going to get infinitely close to it, but never technically get there, but we say that for all intents and purposes it's converging to that value. We say S infinity is that number. Whew! crazy, mind blown. I know, it's bananas. But let's try a problem. And you know what, I'm going to go a step above and beyond. You guys are better than, okay, here's a series, common ratio is 1/2, first term is 2, find the sum. Yeah, we can do that. Sum to infinity, S infinity is 5. And the second term, U2 is negative 6/5. Find the common ratio, oh my. If I knew the first term, I could just say that 5 equals that U1 over 1 minus R, and I'd be done. That'd be great. But unfortunately, yeah, I don't know the first term. I know the second term. And oh, how are we going to find the first term? Well, we would need the common ratio to get to the first term from here. Well, we're going to have to use our rule for a geometric sequence. So this second term is U1 times R to the 2 minus 1, or just R to the first, better known as just R. Well, now we have a system of equations, and we can actually solve for one of the two variables and do substitution. Now, I'm trying to find the common ratio. So I'm going to get U1 by itself so I can substitute for that and be ending up with an equation that has R in it. Let's divide by R on both sides. Negative 6 over 5R equals U1. And guess where that's going, ladies and gents? That's jumping over here. We're doing substitution method all day long. 5 equals negative 6 over 5R divided by 1 minus R. Well, how do these fractions combine together? When we divide and then divide again, negative 6 over 5R times 1 minus R. And now it's time to start solving, guys. This is great here. So I'm going to multiply to get rid of the division. So we now have 25R times 1 minus R equals negative 6. Distribute 25R minus 25R squared equals negative 6. We want to get all of our terms to one side. I'm going to move everything to the right, so I have a positive R squared. 0 equals 25R squared minus 25R minus 6. Oh gosh, we could either use the quadratic formula or factor, and guess what, guys? This is factorable. It's factorable into 5R minus 6 times 5R plus 1 is equals 0. R could be 6/5, or R could be negative 1/5. And you're thinking, great, there's two solutions, this is crazy. But there's not two solutions, ladies and gentlemen. This sum to infinity only exists provided that the common ratio is between negative 1 and 1. The absolute value of R must be less than 1. So that means 6/5 is out, and the only solution is that R is negative 1/5. Second example, geometric series, right here, 2 minus x plus 2 minus x squared plus 2 minus x cubed plus da-da-da-da-da-da converges. What values could x be? Okay, so this is a geometric series. The common ratio is 2 minus x. And since it converges, that means we know the sum to infinity exists. And the only way that can exist is if the common ratio, if its absolute value is less than 1. Well, how do we solve something like this? Sidebar, absolute value of x is less than 2. This means the distance from x, or the distance from 0 on a number line, has to be less than 2 units. So here's 0. I want x to have a distance that's less than 2. There's 2. Any number in here will have a distance less than 2 from 0. But any number down here also would have a distance of 2 or less from 0. So that means x could be between 2 and negative 2, excuse me. We're going to use that same idea here. This stuff, this 2 minus x, has to be less than 1 unit away. So that stuff needs to be less than 1, but it also could be greater than negative 1. And how do we solve something like this? Well, we'd subtract 2 from there and there. Let's pretend we're ignoring this. Let's say we're just solving this. We'd subtract 2, and then we have negative x less than negative 1. Divide both sides by negative 1. X is greater than, we turn the inequality around, 1. But, hold on, there was actually more to this problem. While I was solving that, I just subtract 2 from both sides. So instead of ignoring one side and pretending that it's not there, let's remember to include it. So if we subtract 2 from the middle to get x by itself, we have to subtract 2 over here also. We have negative 3 less than negative x less than negative 1. And if we're dividing by negative 1 here, we have to divide by negative 1 here. So 3 is greater than x is greater than 1. So, let's turn this around the way we're used to reading it. X has to be between 1 and 3. And as long as x is between 1 and 3, this series will converge to a particular value for a sum. Any other x, and we'll be getting terms that diverge and don't converge to a particular value. Any other number of x beyond 1 and 3, well, that's going to get us something like this sequence here, 1, 2, 4, 8, where the sums are getting bigger and bigger and bigger, and they are diverging as opposed to converging like the second one. So, a little bit of a brain stretch with this one. It's an awesome, cool idea, and it's something that's very unexpected. I hope that you really have fun with this.